Good morning, evening, or afternoon, class. We've been wrapping up our textbook learning when it comes to our Chapter 3, Investigation into Linear Systems. So now we're going to kind of switch topics, but it's a natural extension of our linear systems with matrices. Okay, we've got this fancy word matrices. What is a matrix? Why is it important to our life? So our first slide is, what the heck's a matrix? We have a picture of a matrix. I'm also going to describe it using words. A matrix is a rectangular array of variables or constants in rows and columns, usually enclosed by a single set of brackets. In a matrix, the numbers or data are organized so that each position in the matrix has a purpose. Even you might not know this, but you've been using matrices every day. If you opened up your phone this morning to check what time it was, check your friends' text messages, check Facebook, check Snapchat, check Instagram, all those things you check in the morning before you even leave bed, your phone's been using matrices. Every single picture in your phone is encoded as a matrix, where each dot, each data entry tells the camera, tells your computer, tells your phone the brightness, what color that pixel is supposed to be. And so if we ever want to go into computer science, we need to have an understanding of how our matrices function. So how do our matrices function? Well, we need to be able to talk about the size of a matrix. So when I talk about a matrix, just like when we're doing linear systems, we always talk about rise over run. So we're going to talk about up and down before we talk about left and right. So if I have a matrix, I'm going to talk about its number of rows followed by its number of columns. Dimensions of a matrix, the number of horizontal rows, I'm counting my rows going down, by the number of vertical rows, vertical columns, same idea. So I have a 2 by 2 matrix because we have 2 rows followed by 2 columns. If we had a third row, say I had 5, 6, we'd have 3 by 2. If this is still confusing, pause the video, take a moment, let this sink in, because it's going to become very important to other ideas that we deal with later. And so, since we have this idea of talking about our data in terms of rows and columns, we can talk about each number with those row and column designations. So each number or entry in a matrix, we call that an element of the matrix. Element's a big fancy math word that says it belongs there. So these numbers belong to the matrix. If I talk about it, say I have the matrix A, I'll use a capital A for my matrix. Call this matrix A. In each data entry, I'll use a little a lowercase a. The first number will represent which row it is in. The second number will tell me which column it's in. So the number 2 is in the first row, second column. So I'm going to call it A, because it belongs to A. 1 for the first row, 2 for the second column. Again, if you need some extra time with these definitions, pause the video, rewind the video, make sure that you understand how we can talk about a matrix before we continue going further. Speaking of going further, oftentimes we'll have more than one matrix at a time. If I have more than one matrix, I can say that they're equal to each other, that they are the same matrix if, first, they have the same dimensions, same number of rows, same number of columns, and if all of the entries, all of the numbers are exactly the same, they are equivalent. And so, because we're in an algebra course, we have to do some solving. I've got one matrix, I've got another matrix, and I'm going to say that they're equal to each other. Well, that means that each of the numbers in their respective positions have to be equal to each other. 15 and 15 are the same number, 9 and 9 are the same number, -1, 7, same number. So I can set up a very simple equation. I know that my entry, 4x plus 5, in the first row, first column, has to be equal to 21, because that's the number in the first row, first column. So pause the video, figure out what x is going to equal if I set 4x plus 5 equal to 21. Do the same thing for y. Click on the video to continue to watch me go through the process. 4x plus 5 equals 21. First thing that we do, subtract 5 from each side. Let me write it up here so it's a little easier to see. First thing we do, subtract 5 from both sides. 21 minus 5 is going to give us 16. 4x is equal to 16. And we can see from here that x has to equal 4. This is an Algebra 1 problem. We should be good at solving two-step equations. Let's do a similar thing for y. I know that the number in the second row, second column, has to be equal to the number in the second row, second column. So let's set up this equation. Negative 2y plus 3, negative 2y plus 3, set equal to y minus 12. Let's collect all our y's on the same side of the equation. I'm going to put them on the right just because I like to deal with positive numbers. So let's add 2y to both sides. I'll get 3y on the right. And so I want all my y's to be alone, so let's move the negative 12 over to the left. I have a minus 12, so let's add 12 to both sides to get 3y equal to 15. And from here, it's easy to see that y must be equal to 5. Check your answers. Did you get the right solution? I'm sure you did, because we're all brilliant, smart mathematicians. So we can set matrices equal to each other. We can do a whole slew of other operations with our matrices as well. The first operation we're going to look at is matrix addition. If I'm adding matrices together, again, they have to have the same dimensions. Most of the operations I do depend on the dimensions. We'll see this with multiplication in a kind of a different way. And it's a very natural idea to add or subtract these. To find the sum or difference, we add or subtract the corresponding entries. And so we've started the operations for us. We can see that if I add A and B together, first row, first column, plus first row, first column, equals the sum of the first row and the first columns. 0 minus 10 is negative 10. This should not come as a surprise. If we look at it in the subtraction sense, 1 minus 4 gives us negative 3. We're just adding where they line up. Again, pause the video, fill in the chart, hit play to check your answer. 0 plus 5 gives me 5. 4 plus 0 gives me 4. 1 plus 4 gives me another 5. Negative 3 minus 7 gives me negative 10. Negative 5 plus 3 gives me negative 2. There's our addition. Let's look at our subtraction. 0 minus negative 10. Now we've got a positive 10. 0 minus 5 gives us a negative 5. 4 minus 0 is still going to give us 4. And we saw from earlier that 1 minus 4 gave us that negative 3 over there. Negative 3 minus negative 7 is the same as negative 3 plus 7, which is the same as 7 minus 3, which gives us a positive 4. And if we have a negative 5 minus 3 gives us negative 8. Take a moment, check your answers. I'm sure you got them right, though. So this is what happens when we look at adding two matrices that have the same dimensions together. So let's entertain the thought, if we have the same matrices from the last example, could I possibly add C to either of these? Okay, what might that look like? When we added A and B together, we went entry by entry. So for C, you might think, oh, well, I'll just add the first column in the first column, and then I'll add the second column, again with the only column. That doesn't quite make sense. If you try to tell a computer to do this, the computer's going to get very angry at you. It's not something that makes sense when we're talking about the data inherent in our matrices. So be very careful. We have to have the same dimensions in order to add or subtract. We've talked about adding and subtracting. What happens if we add a whole bunch of times? Well, that would be multiplication. And so multiplication takes our dimensions and kind of twists them a little bit. And so before we look at matrix by matrix multiplication, let's just look at scalar multiplication. If I multiply a matrix by a real number, we're going to use the word scalar to describe that real number. It's similar to our idea of coefficients in front of variables. We'll just have scalars in front of our matrices. We're going to multiply the scalar by each element of the matrix. So if I start with the matrix A, we have a new matrix A. And I want to take every entry in that matrix and multiply it by -2. So our new matrix, we can see that 5 times -2 gives us -10. Like always, pause the video, work this out, check your answer afterwards. I know we can multiply by -2, so this shouldn't come as a surprise. 9 times -2 gives us -18. 1 times -2 gives us -2. -2 times -2 gives us +4. -11 times -2 gives us a +22. 8 times -2 gives us that -16. 0 times anything, I don't have to worry about that, we'll still stay 0. 1 times -2 is -2. Our last data entry, -15 times -2 gives us +30. Check your answers. I believe we can multiply by -2. For scalar multiplication, this is maybe the only time where the dimensions don't necessarily matter, because I'm just taking one number and distributing it to each entry. Last few things that we want to talk about is our general properties when we're looking at matrix addition. So if I have 3 matrices, they've got dimensions m by n, so I have m rows, n columns. I don't know how many rows, I don't know how many columns, so I'm just going to use m and n as placeholders. Matrices, in terms of addition, are commutative. If I have matrices A and B, I can add them the same as if I flip-flop them B plus A. Our matrices are also associative when it comes to addition. It doesn't matter which order I add my matrices in, as long as I add them all together. Our additive identity would be a matrix that has 0 in all of its entries and has the same dimensions. So let's think about this. If I have a matrix, 1, 2, 3, 4, and I add the matrix 0, 0, 0, 0 to it, am I going to end up with anything different than 1, 2, 3, 4? I will not. So that's how our identity is working in here. Our additive inverse says that for every matrix that we have with dimensions m by n, the matrix whose entries are the opposite of those in A is the additive inverse of A. And we know, in terms of mathematics, opposite means that we are flipping the sign. So if I have the number 1, its opposite is -1, because when I add these two things together, it comes out to be 0. This shouldn't be too shocking to us. This is a natural extension of where our mathematics has led us to this point. So let's look at this additive inverse in action. So we're going to start, let's call it matrix B. I want to start by adding the additive inverse, or writing down the additive inverse, which I'll designate with a minus b. That minus b makes it look just like our scalar multiplication, where I'm taking every entry in b and multiplying it by -1. I don't think we need to pause the video for these entries. 3 times -1 is -3, -2 times -1 is 2, -7 becomes +7, 5 becomes -5. So let's write that down, 7 and -5. If we remember from the last slide, what's the sum of b and its additive inverse? Well, we should get our additive identity. We should get a matrix that has zeros in every single entry. Prove that to yourself. All right, you should be set for your homework now. See you in class tomorrow.